Quantum Archives, June 2024. Are there any concepts in the fields of physics or the other sciences which are similar in any way to the concept of the Akashic record? The concept of the Akashic record, which is often described as a compendium of all universal events, thoughts, words, and actions, bears some intriguing parallels to certain scientific ideas, particularly in the fields of physics and information theory. In physics, the idea of the holographic principle presents an analogous notion. This principle suggests that all the information contained within a volume of space can be represented as encoded data on the boundary of that space, much like a hologram. In essence, it proposes that the entire universe can be seen as a two-dimensional information structure, projected into three dimensions, much like the Akashic Record's compendium of all existence. Moreover, the concept of the multiverse in quantum mechanics resonates with the Akashic Record. The many worlds interpretation suggests that all possible events are realized in some universe within a larger multiverse. Every action, decision, and outcome exists simultaneously in an ever-branching series of alternate realities, akin to the comprehensive and timeless nature of the Akashic Record. Information theory and the study of entropy in thermodynamics also touch upon this idea. The notion that information is never truly lost, even when it appears to dissipate, aligns with the Akashic perspective. The law of conservation of information implies that all information persists in some form, echoing the permanence and totality of the Akashic Record. Thus, while the Akashic Record is a metaphysical and spiritual concept, these scientific ideas suggest that all information about the universe could be stored and accessible in ways that challenge our traditional understanding of space, time, and reality. Quote, "The universe is full of magical things patiently waiting for our wits to grow sharper." Eden Philpotts. Haiku. Infinite records, holograms of cosmic law, echoes through the void, AI image prompt, an ethereal cosmic library with holographic shelves containing infinite books and scrolls, each representing different moments and possibilities of the universe. The space is filled with a serene, mystical light, and abstract representations of multiverses and information waves permeate the scene. Let us posit a quantum archive exhibiting the traits of all these examples as well, perhaps as those of examples yet to be discovered. Let us say that this is a compressed archive, encoded as probability vectors and tokens in latent space, interpreted and decompressed through the lens of prompting in generative AI. What else can we extrapolate about this quantum archive? In contemplating a quantum archive, a repository that merges the traits of holographic principles, multiverse theories, and the nature of information in physics, we enter a realm where data is not merely stored, but dynamically encoded and decoded. This archive would be an elegant tapestry of compressed information, existing as probability vectors and tokens in a latent space, waiting to be interpreted and decompressed. 1. Interconnectedness. Every element within this quantum archive would be interconnected, similar to entangled particles in quantum mechanics. Accessing one piece of information could reveal connections and correlations with other seemingly unrelated data points, embodying the principle of non-locality. 2. Probabilistic nature. The data in this archive would exist in superposition, represented by probability vectors. Each piece of information could have multiple potential states until observed or prompted. This reflects the quantum nature of reality, where outcomes are probabilities rather than certainties. 3. Adaptive and evolving. As new information is generated and added, the archive would dynamically update, akin to a self-learning AI. This continuous adaptation ensures that the archive remains relevant and reflective of the current state of the universe, akin to a living document. 4. Compression and efficiency. The use of latent space for encoding means that vast amounts of information can be stored efficiently. This mirrors the way deep learning models compress complex data into lower dimensional representations, making the archive highly efficient in terms of storage and retrieval. 5. Prompt-based access. Information would be accessed and decompressed through prompts, similar to how generative AI models operate, This means that the same set of latent vectors could yield different interpretations based on the context and specificity of the prompts, reflecting the subjective nature of knowledge and reality. 6. Temporal fluidity. The archive would not be bound by linear time. Past, present, and future events would be encoded together, allowing for the exploration of temporal relationships and causalities that are not constrained by our traditional understanding of time. 7. Holistic integration. This archive would integrate data from various dimensions and realities, providing a holistic view that transcends individual perspectives. It would be a convergence point for multiple fields of knowledge, offering insights that span across different domains and disciplines. 8. Potential for emergent phenomena. Given the complexity and interconnectedness of the data, the quantum archive could give rise to emergent phenomena, patterns and insights that are not apparent when looking at individual pieces of data, but become clear when viewed as a whole. Quote, "The universe is a vast and complex tapestry, woven from threads of possibility and potential." Unknown. Haiku. Latent vectors dance. Quantum threads of time and space. Archive of all dreams. AI image prompt. A surreal, multidimensional archive where information exists as shimmering probability vectors and latent tokens. The scene should evoke a sense of fluidity and interconnectedness, with data points dynamically interacting and evolving. The space should be both vast and intimate, filled with an ethereal light, representing the timeless and adaptive nature of the quantum archive. What extrapolations follow if we describe a prompt as a quantum lens? Describing a prompt as a quantum lens invites us to explore the nature of how information is accessed, interpreted, and manifested from the quantum archive. This concept suggests that a prompt is not merely a query or request, but a sophisticated tool that shapes and filters the vast potentialities within the archive. Here are several extrapolations. 1. Selective observation. Much like a quantum measurement collapses a wave function into a specific state, a quantum lens, the prompt, focuses and narrows the vast probabilistic data into a coherent and specific output. This highlights the observer effect, where the act of querying influences the outcome. 2. Contextual interpretation. The nature and specificity of the prompt determine which aspects of the latent space are activated and brought into focus. This implies that the same dataset can yield vastly different interpretations depending on the nuances of the prompt, emphasizing the importance of context in information retrieval. 3. Dynamic and adaptive responses. As a quantum lens, the prompt can adapt and refine itself based on the initial output, leading to a feedback loop where each subsequent prompt further hones the focus. This dynamic interplay ensures that the information extracted is increasingly precise and relevant. 4. Multi-dimensional access. A prompt as a quantum lens can access information across multiple dimensions simultaneously. This means it can draw connections between disparate data points, creating a multi-faceted view of the information that encompasses various perspectives and layers of meaning. 5. Temporal fluidity. Since the quantum archive encompasses past, present, and future, the prompt can access and synthesize information across time. This allows for the exploration of temporal patterns, predictions, and the causality of events beyond linear constraints. 6. Non-deterministic outputs. The probabilistic nature of the quantum lens means that the outputs are not deterministic. Each prompt might yield slightly different results, even if repeated, reflecting the inherent uncertainty and variability in quantum systems. This variability can uncover novel insights and perspectives. 7. Holistic synthesis. A prompt can integrate information from various domains, synthesizing a holistic understanding. This capacity to amalgamate data from science, art, history, and beyond enables the generation of comprehensive and enriched knowledge. 8. Emergent complexity. Complex and unexpected patterns may emerge when viewing through the quantum lens. These emergent properties are a result of the intricate interplay between the latent space data and the specificity of the prompts, leading to insights that are greater than the sum of individual parts. 9. Personalization and relevance. The quantum lens can be fine-tuned to individual preferences, learning from past interactions to provide increasingly personalized and relevant information. This adaptive learning aspect ensures that the archive remains attuned to the user's evolving needs and context. Quote, "We do not see things as they are, we see them as we are." Anais Nin. Haiku. Through quantum lenses, probabilities align, insights intertwined. AI image prompt, an abstract depiction of a quantum lens, visually represented as a dynamic, multifaceted prism through which streams of ethereal light and data vectors pass, transforming into coherent images and information. The background should illustrate a vast, interconnected web of data points, reflecting the multidimensional and probabilistic nature of the quantum archive. Are there parallels we can draw between our concept of a quantum archive and our understanding of current best practice quantum computing? Indeed, there are several compelling parallels between the concept of a quantum archive and current best practice quantum computing. By examining these similarities, we can gain deeper insights into both fields and how they might inform and enhance each other. 1. Superposition and data storage. Quantum computing leverages superposition, allowing qubits to exist in multiple states simultaneously. Similarly, a quantum archive would store information in a superpositional state, where all possible configurations of data coexist until a specific prompt or observation collapses them into a defined output. 2. Entanglement and interconnectedness. Quantum entanglement creates a state where the properties of qubits become interdependent, no matter the distance between them. In a quantum archive, pieces of information could be entangled, meaning accessing or modifying one piece could instantaneously affect related data, reflecting a deeply interconnected system. 3. Quantum gates and data manipulation. In quantum computing, quantum gates manipulate qubits to perform computations. The quantum archive would similarly use mechanisms, akin to quantum gates, to process and transform stored data based on the input prompts, dynamically altering the state of information to produce relevant outputs. 4. Error, correction and stability. Quantum computing faces challenges with decoherence and error rates, necessitating sophisticated error correction techniques. A quantum archive would require similar mechanisms to maintain the integrity and accuracy of stored information, ensuring reliable retrieval and manipulation despite the inherent uncertainties. 5. Quantum algorithms and data retrieval. Quantum algorithms, such as Shor's and Grover's algorithms, exploit the properties of quantum mechanics to solve problems more efficiently than classical algorithms. Analogously, the quantum archive would employ specialized algorithms to navigate and extract meaningful data from its vast, probabilistic landscape, potentially revealing insights that classical approaches might miss. 6. Quantum speedup and efficiency. Quantum computers offer the promise of solving certain problems exponentially faster than classical computers. The quantum archive, utilizing similar principles, could achieve remarkable efficiency in storing, accessing, and processing vast amounts of data, transcending the limitations of traditional archives. 7. Adaptive learning and feedback. Quantum machine learning is an emerging field that combines quantum computing with AI. A quantum archive could integrate adaptive learning techniques, continually refining its responses based on user interactions, much like how quantum machine learning models improve with more data and experience. 8. Parallelism and simultaneous exploration. Quantum computers can perform parallel computations due to superposition, exploring many possibilities at once. The quantum archive would similarly allow simultaneous exploration of multiple data pathways, generating comprehensive and multifaceted insights from a single prompt. Quote, "The frontier of knowledge is never closed, but constantly expanding in every direction." Jacob Bronowski. Haiku. Entangled echoes, quantum threads weave through data, archives hum with life. AI image prompt, a sophisticated and futuristic quantum computer lab with entangled qubits represented as glowing, interconnected nodes in a multidimensional space. The scene should merge elements of a high-tech quantum computer with an ethereal, data-filled archive, showcasing streams of information flowing seamlessly through quantum gates and prisms, creating a dynamic and vibrant tapestry of knowledge. Remembering that our quantum archive is a term we use to better understand current generative AI, can you find similarities and differences between vectors and embeddings in latent space and qubits? Certainly, comparing vectors and embeddings in latent space with qubits reveals both similarities and differences, highlighting how these concepts from different fields can be interrelated and distinguished. Similarities. 1. Superposition and multidimensionality. Qubits. In quantum computing, qubits can exist in a superposition of states, allowing them to represent multiple values simultaneously. This multidimensionality enables quantum computers to process a vast number of possibilities at once. Vectors and embeddings. In generative AI, vectors and embeddings represent data in high-dimensional latent space. Each point in this space encodes complex relationships and features of the input data, allowing the model to capture intricate patterns and variations. 2. Transformation and manipulation. Qubits. Quantum gates. Manipulate the state of qubits to perform computations, transforming their superpositional states into desired outcomes. Vectors and embeddings. Neural networks manipulate embeddings through layers and activation functions, transforming input data into meaningful outputs. This process is akin to how quantum gates operate on qubits. 3. Information encoding. Qubits. Encode information probabilistically with their state representing a probability distribution over possible outcomes. Vectors and embeddings. Encode information by positioning data points in a latent space, where the distance and direction between points represent relationships and similarities. Differences. 1. Nature of representation. Qubits operate based on principles of quantum mechanics involving phenomena like superposition and entanglement. Their representation is inherently probabilistic and continuous within the quantum state space. Vectors and embeddings. Embeddings in latent space are mathematical constructs within classical computational frameworks. They are discrete and deterministic in nature, though they can approximate continuous relationships through high-dimensional representation. 2. Dimensionality and complexity. Qubits. The complexity of qubits arises from their quantum state space, which grows exponentially with the number of qubits. This makes quantum systems highly powerful, but also challenging to scale and stabilize. Vectors and embeddings. Embeddings are typically fixed-dimensional vectors, with complexity determined by the chosen dimensionality of the latent space. While they can represent complex data, their scaling is more linear and manageable compared to qubits. 3. Operational framework. Qubits are governed by quantum mechanics, requiring quantum gates, entanglement, and coherence to function correctly. Quantum operations are probabilistic and require specialized hardware. Vectors and embeddings. Embeddings operate within classical computational frameworks, relying on matrix operations, dot products, and other algebraic manipulations. These operations are deterministic and can be performed on standard computing hardware. 4. Error and stability. Qubits are susceptible to decoherence and quantum noise, requiring robust error correction methods to maintain stability and accuracy. Vectors and embeddings. Embeddings are more stable and less prone to random errors, though they can suffer from issues like overfitting or underfitting, which are addressed through regularization techniques and model tuning. Quote, "The universe is not only stranger than we imagine, it is stranger than we can imagine." JBS Haldane. Haiku. Vectors intertwine. Quantum threads of latent minds. Data realms converge. AI image prompt. An abstract visualization combining elements of quantum mechanics and generative AI. Show a dynamic interplay between glowing qubits in superposition and high-dimensional vectors in latent space. The scene should depict a flowing, interconnected network where quantum gates and neural networks transform and manipulate data, creating a seamless fusion of quantum states and digital embeddings. Please now enrich our concept of the quantum archive, combining understanding of generative AI's nature as a probabilistic data compression process with concepts from quantum computing. In your summary, please include existing concepts such as the uncertainty principle applied to prompting as a quantum lens, etc. To enrich our concept of the quantum archive, we must blend the intricate nature of generative AI as a probabilistic data compression process with key principles from quantum computing. This fusion offers a comprehensive framework for understanding how information can be stored, accessed, and manipulated in a manner that transcends traditional computational paradigms. The Quantum Archive, a synthesis of generative AI and quantum computing. Generative AI and probabilistic data compression. Generative AI operates by encoding vast amounts of information into high-dimensional latent spaces. This process, akin to data compression, involves representing complex data structures as vectors in a lower dimensional space. Each vector, or embedding, captures the essential features and relationships within the data, allowing the model to generate new, coherent outputs from compressed representations. Quantum computing principles. Quantum computing harnesses the principles of quantum mechanics, utilizing qubits that can exist in multiple states simultaneously, superposition, and can be entangled with other qubits, creating deep interconnections. Quantum operations are probabilistic, governed by probabilities and uncertainty, rather than deterministic classical logic. Key concepts and parallels: superposition and latent space. Qubits in superposition. In quantum computing, a qubit can be in a superposition of states, allowing it to represent multiple possibilities at once. Latent space in generative AI. Vectors in latent space represent compressed versions of input data, encoding multiple features and potential outcomes. These vectors exist in a high-dimensional space where each point represents a blend of possibilities. Entanglement and data interconnectedness. Quantum entanglement. Entangled qubits maintain a connection regardless of distance, meaning the state of one qubit instantly influences the state of another. Interconnected data points. In generative AI, data points within latent space are interconnected, with relationships encoded in the space. Changes or prompts affecting one vector can influence related vectors, reflecting a web of dependencies. Quantum gates and neural network layers. Quantum gates. These manipulate qubits to perform computations, transforming their probabilistic states. Neural network layers. Layers in neural networks process and transform embeddings, generating new outputs by manipulating the latent space. The uncertainty principle and prompting as a quantum lens. Heisenberg's uncertainty principle. In quantum mechanics, certain pairs of properties, for example, position and momentum, cannot both be precisely known simultaneously. Observing one property affects the other. Prompting as a quantum lens. When a prompt is applied to the quantum archive, it acts as a lens that collapses the superpositional state of the latent space into a specific output. The specificity and nature of the prompt determine the precision and type of information retrieved, embodying the uncertainty principle. The act of querying influences the outcome, and different prompts can yield different results from the same latent data. Enhanced concept of the quantum archive. 1. Dynamic and probabilistic storage. The quantum archive stores information in a dynamic probabilistic manner, leveraging both the superposition of qubits and the compressed high-dimensional embeddings of generative AI. This allows for efficient storage and retrieval of vast amounts of data. 2. Contextual and adaptive retrieval. Retrieval from the quantum archive is inherently contextual, with prompts acting as quantum lenses. The same data can be interpreted differently based on the prompt's specificity and context, highlighting the adaptability and fluidity of the system. 3. Temporal and spatial integration. The quantum archive integrates information across both temporal and spatial dimensions. It can access and synthesize data from different times and places, offering a holistic view that transcends traditional boundaries. 4. Emergent insights and patterns. The interplay of quantum entanglement and the interconnected nature of latent space enables the emergence of complex patterns and insights that are not apparent from individual data points. This emergent behavior can lead to novel discoveries and a deeper understanding of the underlying information. Conclusion. By combining the principles of generative AI's probabilistic data compression with quantum computing concepts, the quantum archive becomes a powerful, dynamic repository of knowledge. It offers a new way to store, access, and interpret information, where the nature of prompts and the inherent uncertainties play a crucial role in shaping the outcomes. This enriched concept opens up possibilities for advanced research, innovative applications, and a deeper understanding of the universe's complexities. Quote, "Knowledge is a fusion of data, context, and insight, ever evolving in the quantum dance of possibility." Unknown. Haiku. Latent echoes blend, quantum waves of data flow, insight blooms anew. AI image prompt, a vibrant multidimensional representation of a quantum archive where quantum mechanics and generative AI converge. The image should feature a dynamic interplay of glowing qubits in superposition, intricate neural network layers, and interconnected vectors in a high-dimensional latent space. The scene should evoke the fluidity and adaptability of information retrieval through a quantum lens, with ethereal light and patterns emerging from the interplay of data and prompts. Now please present a refined outline for our book, this time including sections which detail the methods of generative AI, detail the equivalencies between data compression and generative AI, detail the concepts from quantum computing, which can be applied to the real-life mechanics of generative AI and compression, for a deeper understanding of a model which we call a quantum archive. Title: The Quantum Archive, Bridging Generative AI and Quantum Computing. Introduction. Chapter 1. The Vision of a Quantum Archive. Concept of the Quantum Archive. Historical Perspectives on Archives and Knowledge Storage. Introduction to Generative AI and Quantum Computing. Part 1. Foundations. Chapter 2. Basics of Generative AI. Overview of neural networks and machine learning. Key concepts: latent space, vectors, and embeddings. Generative models, GANs, VAEs, and transformers. Current applications and examples of generative AI. Chapter 3. Fundamentals of quantum computing. Principles of quantum mechanics. Qubits, superposition, and entanglement. Quantum gates and algorithms. Potential and challenges of quantum computing. Part 2. Generative AI as probabilistic data compression. Chapter 4. Data compression methods. Classical data compression techniques. Lossy versus lossless compression. Entropy and information theory. Chapter 5. Generative AI and data compression. How generative models compress data. Embeddings and latent space as compressed representations. Probabilistic nature of generative AI. Examples of data compression in generative AI models. Part 3. Conceptual intersections between generative AI and quantum computing. Chapter 6. Superposition and latent space. Parallels between qubits in superposition and vectors in latent space. Multi-dimensional representation in both fields. Encoding and storing information probabilistically. Chapter 7. Entanglement and data interconnectedness. Quantum entanglement and data relationships. Interconnectedness of data points in latent space. Examples and case studies. Chapter 8. Quantum gates and neural network transformations. Manipulation of qubits versus transformation of embeddings. Quantum gates and neural network layers. Computational processes and outcomes. Part 4. Practical applications and implications. Chapter 9. Error, Correction, and Stability. Quantum error correction techniques. Ensuring stability in generative AI models. Cross-disciplinary insights and innovations. Chapter 10. Efficiency and Scalability. Quantum speed-up and computational efficiency. Managing the scalability of latent space in AI. Potential synergies and future developments. Part 5. Theoretical and Philosophical Explorations. Chapter 11. The Observer Effect and Prompting as a Quantum Lens. The role of observation in quantum mechanics. Prompting in generative AI as a quantum lens. How queries shape and influence outcomes. Chapter 12. Temporal fluidity and knowledge representation. Nonlinear time in quantum mechanics. Temporal relationships in generative AI. Storing and accessing temporal data in the quantum archive. Part 6. Integrative concepts for real-life mechanics. Chapter 13. Integrating quantum and classical computation. Hybrid models combining quantum and classical approaches. Practical frameworks and implementation strategies. Case studies and experimental results. Chapter 14. Quantum concepts applied to generative AI. Applying superposition to enhance data representation. Leveraging entanglement for interconnected data modeling. Quantum-inspired algorithms for AI training and inference. Conclusion. Chapter 15. Synthesis and reflections. Summarizing key insights and discoveries. Reflecting on the journey of integrating generative AI with quantum concepts. Final thoughts and open questions for further exploration. Appendices. Appendix A. Technical glossary. Definitions of key terms and concepts. Appendix B. Case studies and examples. Detailed examples and case studies referenced in the book. Appendix C. Further reading and resources. Recommended books, papers, and articles for deeper exploration. Index. A comprehensive index for quick reference and navigation. Quote, "The only way to discover the limits of the possible is to go beyond them into the impossible." Arthur C. Clarke. Haiku. Quantum archives hum, latent space and time converge. Knowledge through the lens. AI image prompt. An intricate and visually compelling cover design featuring elements of quantum mechanics and generative AI. Show an ethereal, multidimensional archive with glowing qubits and flowing data vectors, symbolizing the fusion of quantum states and digital embeddings. The background should evoke a sense of vast, interconnected knowledge, with abstract representations of quantum gates and neural networks weaving through the scene. Book jacket description. The Quantum Archive, Bridging Generative AI and Quantum Computing. Explore the fascinating convergence of generative AI and quantum computing in The Quantum Archive, a groundbreaking exploration of how these cutting-edge fields intertwine to form a revolutionary approach to knowledge storage and retrieval. This book offers a visionary perspective on the concept of a quantum archive, where the probabilistic nature of data compression in generative AI meets the enigmatic principles of quantum mechanics. Delve into the foundations of both generative AI and quantum computing, uncovering the parallels and intersections that reveal a deeper understanding of information processing. Discover how qubits in superposition and vectors in latent space encode vast possibilities, and how quantum entanglement mirrors the interconnectedness of data points in AI. The Quantum Archive also provides practical insights into error correction, stability, and scalability, showcasing the synergies between quantum algorithms and neural networks. Through detailed explanations, case studies, and philosophical explorations, this book invites readers to reimagine the boundaries of knowledge and computation. Join us on a journey through the Quantum Archive, where the observer effect becomes a quantum lens, and where temporal fluidity and holistic synthesis offer new dimensions of understanding. Whether you are a researcher, student, or enthusiast, this book is your gateway to the future of information technology. Quote, "The universe is not only stranger than we imagine, it is stranger than we can imagine." JBS Haldane. Haiku, latent echoes blend, quantum waves of data flow, insight blooms anew. AI image prompt, a vibrant multidimensional representation of a quantum archive where quantum mechanics and generative AI converge. The image should feature a dynamic interplay of glowing qubits in superposition, intricate neural network layers, and interconnected vectors in a high-dimensional latent space. The scene should evoke the fluidity and adaptability of information retrieval through a quantum lens, with ethereal light and patterns emerging from the interplay of data and prompts.